Okay, hello everyone. We continue chapter 10. Okay, this time it will be section 10.3. Okay, it's about permutations and combinations. Okay, let me tell you immediately the go to the subject. Okay, first I will write formula, and then I will explain this formula, but you have to understand the logic behind this formula, because that is the essence of what we are talking about. So permutations and combinations are just extension of the standard fundamental principle, or the product rule, or multiplication rule. So let me solve two following problems. Okay, problem one. Okay, you have, there are 8 people. I will just write very shortly. 8 people. Okay, they choose 3 positions. Okay, choose 3 positions. Okay, president. Okay, president, it's number 1. Then vice president and secretary. In how many ways? Can this choice can be arranged? Okay, so okay, we'll solve this problem just immediately, but first I formulate another problem, and you have to see the difference between these 2 problems. Okay, problem number 2. Again, 8 people. 3 positions. Okay, they choose a committee of 3 people. 3 people. And once this committee is chosen, okay, then inside this committee, okay, 3 people will just figure out they will choose who is president, who is vice president, who is secretary. And question is the same: how many ways? Can this arrangement, let me just, choice, okay, here I wrote choice, but let me just write arrangement. And this one, okay, also maybe arrangement. Arrangement could be arranged. Arrangement could be done. Can this be done? Or be made, okay. So 2 problems, and they look alike, but actually they are very absolutely 2 different approaches. Okay, so let's solve first problem. Solution. Okay, solution to number 1. Okay, let's work in the same way as we did before for solving problem of that kind and using the multiplication rule. So we have 3 positions, okay, and we have 8 people. Remember last time I told about the alphabet. The alphabet is just not a set of characters. and we just choose these characters and put like, call these characters alphabet. No, it doesn't matter whether that real alphabet or numbers or digits, or maybe people. So we have an alphabet with 8 people. So how many possibilities are there to choose the president first? Okay, how many ways? So 8 people, then how many ways? 8, truly. So let me just write letter P, president, 8 possibilities. Okay, 8 possibilities. Now what happens? Once the president is chosen, how many people are left over?
7.
7. So therefore, for vice president, we have only 7 possibilities. And after that, we have a choice out of 6 people for the secretary. Okay, and now the answer is clear. We just apply this fundamental counting principle or just multiplication rule. All these events are independent. So these 8 people chose president independently, then after that vice president independently, and after that secretary independently. Okay, let's look. What if I started? What if they started for their choosing not the president first, but vice president? In this case, the number of ways to choose vice president would be 8, and after that for the president would be 7, and for secretary 6. So the same number but located in different position. Nevertheless, the final answer will be the same. Likewise, if you start with secretary, you have 8 possibilities to start with to choose secretary. If you start with it, then maybe 7 ways to choose president, and then 6 ways to choose vice president, or 8 ways to use secretary, 7 ways to choose vice president, and 6 for president. Anyway, the product will be that one. Why? Because in the beginning you have, if you consider the tree, okay, let's write here. Okay, so you have 3. Okay, you have 4. You have a fan of 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8. So you have 8 possibilities for president. Let's write. So either this guy is president, or that guy is president, or that one, this one, president. So you have 8 possibilities. Now, after that, for each one, you have to draw 7 segments, and right here vice president, right? VP. Okay, I will not write it down. So do the same in each one. Now, after that, once you draw that extension of the 8 branches with 7 extensions, okay, 7 extensions for each, you have already 56. And after that, each one out of 56 must be extended into 6 different ways. So we have to multiply by 6, and we find the number of leaves in the end. And so that number is, what is that number? 56 times 6. What is that? 336. 336 ways. So many ways to choose president, vice president, and secretary. Okay, now let's go to the second problem. Okay, you will see a little bit later how to rewrite this product in factorials. So far you don't see factorial, but in a couple of minutes you will see how this product will be converted into the factorials. Now, consider the other one, that problem. What do we have? In this case, we don't know who are in the committee. Okay, we know actually, so we just pick 3 people, or we pick 3 places, 3 chairs, and we sit, so 3 people will sit at these 3 chairs. So if you could say, so the same reasoning happens here. No. In the beginning, we know that the first guy is the president, and we know that the second guy is vice president, so they're distinguishable. They're distinguishable. And the third one is also distinguishable. So now, actually, when we choose a committee of 3 people, we have so we can use the following. So either president, vice president, and secretary. Okay, we don't know the order, or so we know only this set. But if you want to create an order, you have to write either this or president, secretary, vice president, or vice president, then president, and then secretary, or vice president, secretary, and president. We have already 4 of them. And finally, on the first place, secretary, president, and vice president, or secretary, vice president, and president. Okay, so therefore, when we choose 3 positions, okay, and then after that we just apply that one of those 6 possibilities, then only after that we'll get 336. So if we denote in how many ways can this arrangement be done. So suppose there are x, so our number is x. So we take x, possibilities, okay, then and then after that each one should be extended in 6 different ways. So if you multiply it by 6, only in this case you get 336. Okay, so you see the difference is as follows. Here we had directly, we knew that the first guy has his name, okay, say Biden, and vice president Harris, and secretary I don't remember who. Okay, but in this case you know, okay, you personifies each person, yeah. In this case, we just choose positions for 8 people. So the number of positions will be less than the number found in the previous case, okay, 6 times. So therefore, from here we find that x equals 336 divided by 6. And so the answer is, by the way, instead of dividing you can write 8 times 7 times 6 divided by 6, cancel out, and you get 56. So therefore 56 ways are there to arrange, to choose a committee of 3 people, or just 3 places. So let me just write now, answer here is 56, okay, and answer here 336. Okay, it wouldn't be interesting if some numbers, okay, whatever, so some other problem could be solved in the same way, will be found different numbers, but now we want to establish the general law. Okay, let's write the first number, the first answer, 336, which is 8 times 7 times 6, as follows. We want to create factorial. Okay, how to create 8 factorial? We have to multiply 8, 7, 6, 5, 4, 3, 2, and 1, from 8 to 1. But there is no 5, 4, 3 to 1. We can artificially introduce this 5, 4, 3 to 1. Okay, write this one, 8, 7, 6, 5, 4, 3, 2, and 1. But because we spoiled our product, we multiplied by many numbers, we have to divide by the same numbers. Okay, so it's a little trick. So usually you have deal with fractions and you reduce fraction, but sometimes it makes sense to multiply fraction by some number to see general regularity. So when you multiply this one, you get the following. What's written in the numerator? What's written in the numerator? 8
factorial.
Factorial, yes. 8 factorial. What's written in the denominator? 5 factorial. Okay, so we got a very beautiful and short formula. 8 factorial over 5 factorial. Now, what is 5? 5 is just how many factors did we add? 1, 2, 3, 4, 5, right? But before we had only 3 factors, and exactly 3 positions we chose. So that could be written as follows: 8 factorial, and let us write number 5 as 8 minus 3. 8 minus 3 is 5, right? So then we just surround with parentheses and then write factorial. So therefore that number 336 is not interesting, but that number is very interesting. It's 8 factorial divided by 8 minus 3 factorial. Okay, and let me just go immediately to this problem and generalize and write the general formula. So what is the general? Okay, let's write problem number 1, but I will now use different number, not 8, any number. So let me just write n people. Okay, and then choose not 3 people, 3 positions, okay, but choose k positions. K positions. And now I add one more word, is distinguishable. Distinguishable. What does it mean? It means that order is important. Okay, the order is important. We know that first is president, vice president, secretary, or we know that the other way around, but we know that beforehand. And that's why the number of ways in this case is denoted as P permutations, okay? And then we just write number n on the left side and k on the right side. So this is also one symbol. Usually in mathematical books, instead of permutations, it's written arrangements. And denoted instead of P, it's letter A. But because your book uses P, I will also use P. And many calculators use P, right? Okay, that's why it is. So what is the formula? Okay, now let's look again what we found. We found 8 factorial, which is the number of people, factorial, and then 8 minus what's given. Okay, that will be the answer. So we take n factorial divided by n minus k. Don't forget to write parentheses. First you subtract, and then you find the factorial. So therefore you have so many, and that number is 336 for n. So in this case n equals 8, k equals 3, n minus k is 5. So that's what you know. And that number can be written as follows. This number is P, okay, 8, permutation 8, so 3 out of 8. Okay, so therefore order is important and the formula is this one. Now problem 2. Again, we have n people, and now so now we choose. Okay, let me just write instead of committee, choose k places or positions, only positions, but we don't know who is president, who is vice president, and so on. Okay, positions, places. Order is not important. Order is not important. Okay, is not. You see the difference. Here is important, and this is not important. And that's why we get this number smaller than this number is smaller than that number. Okay, so here you have P and K. The formula is n factorial over n minus k factorial. Not k, but n minus k. Now let's look what we'll have here, 56. Okay, it's 336 divided by 6. Okay, let's write x equals 336 over 6. But what is 6? 6 is the number of ways to arrange the chosen people inside that group, inside the chosen group. We can choose this group in 56 possibilities, and inside that group we have 6 possibilities to arrange the order. But what is 6? Okay, we solved the same problem as before. On the first place you put either president or vice president or secretary. Or you can put secretary, then vice president, and president. So we have 3 positions, and we have a plan. Okay, so these 3 people meet and they have to figure out who is president, who is vice president, and secretary. Okay, they say, okay, let's put on the first place, let's first president. How many ways can we do this? We have 3 people, right? So therefore 3 possibilities. Okay, the same reasoning as before. 3 possibilities. Now for vice president, next one, we have only 2 possibilities because 1 person is already chosen. And finally for the secretary we have 1. So 3 times 2 times 1, which is 6. Okay, that's why we got 6. It's not just writing the list, but we know that 3 times 2 times 1. Or we can put on the, we have to make a plan and then just go along this plan. We can write along our plan some other plan, choose for example secretary, 3 possibilities, then for president will be only 2 possibilities, and again 1. So we have the same product, the same number of possibilities, but this time we'll not write 6. We just write this as a 3 factorial. Okay, so therefore x equals 336 equals, and let me just write the following. Instead of 336, we know already the formula. Okay, remember I taught you to write equality sign and then the fraction in between of. Only in this case you will not make a mistake. So what's written on the top? 336, but 336 is 8 factorial over 5 factorial. So let's write it down. 8 factorial divided by 5 factorial. Now what do we have in the denominator? Instead of 6, we just write 3 factorial. And then you write equality, okay? And what do we have here? How to write this fraction? So we have to sit on that fraction and push it down. Then 5 will go down, 8 will be in the numerator, okay? 5 will go down, and we can write on either on the left side or on the right side. Let me write on the right side. So 3 factorial, and let's also not take parentheses, times 5 factorial. Okay? And now we see the following. 8 we see here. We see 3, and also we see 5, which is 8 minus 3. In the previous formula, we saw only 8 and 8 minus 3. Okay? Here you see both of them, 3, 5. It's more symmetric. Okay, so this is the formula. And let me just write it down. And it's called the number of combinations. And we know it as C, like choice, and K, but also the standard notation, and it's written in the very small letters in your book, in the footnote. This is the same, N, choose K. N, choose K. So that is this number. And the answer is a little bit more complicated, but much more symmetric and much easier to memorize. So it's n factorial, okay, n. Then you write k factorial. And after that, okay, it's not enough room, so it's probably number 2. Okay, and after that, multiply by n minus k factorial. So this is the formula. If n equals, okay, in this case, what do we have? We have here n factorial over k factorial times 5 factorial. Let me omit, times n minus k factorial. So in this case, n equals 8, k equals 3, and n minus k is 5. Okay, very symmetric formula. Remember, I a little bit hesitated where to write 5 factorial, on the left side or on the right side. I put it on the left side. And that's why it's called 8, choose 3. So let me just write down. This one is 8, choose 3. But imagine that somehow I moved this 5 down to the left. In this case, I would get 8 factorial over 5 factorial times 3 factorial, which is the same, of course. Right, parentheses. Okay. But now the meaning of that expression is different. It's according to that, what you have to write n first, which is 8. Okay. Then k factorial, which is 5. And what's left over, n minus k, will be 3. So it will be 8, choose 5. And so if I write 5 factorial on the right side, I have 8, choose 3. If I write 5 factorial below on the left side, it will be 8, choose 5. But the numbers are the same. Okay? That number is equal to this number. So the product is the same in the denominator, yes? So these two numbers are equal, and we got the following expression: 8 choose 3 equals 8 choose 5. This can be written generally as follows. Let me just write down. So we can write this as n choose k equals n choose n minus k. Okay, so 8 choose 3 equals n choose 8 minus 3, or 8 choose 5 equals 8 choose 8 minus 5. Okay, so we have this fundamental principle, and another fundamental principle is principle of symmetry. Symmetry. Okay, and the number of permutations. Okay. That one we call combinations. Okay, let me just write combinations. Combinations. And what is combinations? Order is not important. Okay, I told you many times when we learned set theory that set is kind of a bag of things. And if we just shake the things, they can permute, but the bag okay, the objects, the objects will not change. It will be the same bag with the same Christmas toys, okay, kind of. So the order is not important. That's why we attach the word sets, okay, sets, okay. You have to associate sets with the n choose k. The number of combinations, okay, so the number of combinations, when you pick some number of positions without names, without any labels, then you have to use, okay, no order, and so therefore you have sets. And sets corresponds to the n choose k, in which case you have two factors in the denominator, k factorial and n minus k factorial. N factorial is in both cases the same. Now here, that number, how to get this number from that one? You have to remove k factorial. Okay, it's easy to say that I take eraser and erase. What I have to do mathematically? I have to multiply by k factorial. If I multiply by k factorial will be cancelled out. So we got the following, another fundamental result: the number of arrangements where the order is important, like president, vice president, and so on, equals, if you rewrite in combinations, you must multiply by k factorial. Okay, this is a formula, kind of abstract formula, but if you understand what the whole process here is, you should understand. For example, if I write P83, the number of arrangements 3 out of 8, okay, I take combinations out of 3 out of 8 with no faces, kind of. So president, vice president, and secretary have faces. We can distinguish them. But in this case, you kind of, okay, you can consider three marbles, okay, with labels. One label is president, another vice president, secretary. So imagine that you put 3 white balls with the labels president, vice president, and secretary inside an order. And you just pick one of them. It could be secretary, say, second one could be president, and the second one will be vice president. How many ways could you do this? 3 factorial ways. But if you remove the labels, then you will take, so first guy will take one marble, the second the same marble of white color and the same size, and the third one also the third white. So this number, order is important. If order is not important, we have to multiply by the number of orders, which is 3 factorial. This is number of orders or arrangements, permutations, number of permutations of 3 objects. Okay. Okay, this is the same as in here. We multiply by k factorial, and we get a number of permutations of k objects. Now, these k objects must be distinguishable. This time, distinguishable. Only in this case you have 3 factorial. Okay, now, what is the difference between 8, 7, and 6, and 8 factorial? If, for example, you want to choose president, vice president, secretary, and who else? Who is there? Some, okay, senior director, then vice director, and so on, up to the last person. Then in this case you would say 8 possibilities for this, 7 possibilities for that, 6 for this, then 5 for that, and so on, up to 1, in which case you would get 8 factorial. But because you interrupt yourself after the third position, you have to divide by another factorial, but this factorial not 3 factorial, it says 8 minus 3. What is left over? So 3 people here, 5 are left over, so you divide by 5 factorial. Okay, got it. So it's written on the page 5, page 6. Let me just and now let's go to page 7. Okay, I hope that I explained pretty clearly. Did I? Okay, why we have to divide by k factorial or n minus k. So let's go to the particular problem in your pages. So evaluate each permutation. Permutations. Okay. A. Permutation 3 out of 5. Okay, what we have to write? 5 factorial over not 3 factorial, but 5 minus 3. And then we write factorial. So it will be 5 factorial over 2 factorial. Okay, then you can calculate, if you know the number, you can write 120 and divide by 2. The answer is 60. But it's better to solve this problem not like, for small numbers it's okay, but for big numbers you will see. Could be calculated as follows. What is 5 factorial? 5 times 4 times 3 times 2 times 1. And we have to divide by 2 factorial, which is 2 times 1. So cross it. And you have 5 times 4, 20 times 3, 60. A little bit easier, but when you have to deal with factorials, big numbers, then just, it's not only my advice, but sometimes it's only one way to solve this product and ratio using your calculator, even computer. So instead of multiplying big massive of numbers, you just multiply only sum of them. Okay, second problem B is P 6 of 6. Let me just look what is that. Now what is that? So you take 6 factorial and divide by 6 minus 6. So in this case it's n, and that is k. Okay, and then write factorial. What is that? 6 factorial over 0 factorial. You know that one are not allowed to divide by 0, but this is 0 factorial. And 0 factorial is not 0, it's 1. So therefore it's 6 factorial divided by 1, by definition. Okay, 6 factorial is 6 times 5, 4, 3, 2, and 1, divided by 1, which is the same, and the answer is 720. So 720. By the way, so it's not written here, but let's calculate what is the 6 choose 6. 6 choose 6. Okay, this is the same as the previous number. Let's write 6 factorial. Now you have to write k. This is k. You write divide by 6 factorial and times the product, which is 0 factorial. That n minus k. You see, in the permutations, only the second part is participated, 0 factorial. But here it's that one. And now you see, cancelled out, and the answer is only 1. So when you have 6 positions and you pick those 6 positions out of 6, you have only one choice to pick them. Only one choice. Okay, so you have 6 chairs. Okay, you pick them together. It's one possibility to choose, and this is the answer. But if after that you suddenly found that each chair has a label 1, 2, 3, 4, 5, 6, then you start permute them. And when you start permute, you will be able to do this with 6 factorial ways, which is 720 possibilities. You see the difference? No order here, you just choose, okay, 6 desks, okay, 6 chairs at once. And this one, you just rearrange them and found something like that, something like this. It's only 6, but in this case, if you exchange not three chairs with labels, but 6, it can be done with 720 ways. 6 factorial equals 720 ways. Okay, so let's solve one more problem. The number of IDs. Okay, I erased that one. Okay, so example, page number 8, IDs. How many IDs are there? Okay, how many ways can you select 2 letters followed by 3 digits? Okay, let's write. So this is letter, followed by 3 digits. Okay, digit. Okay, if repeats are not allowed, no repetitions. No repetitions. Okay, so let's solve in 2 different ways. One way is your standard way. How will you solve this problem if you don't know anything? And by the way, you have come up with the same answer, even if you forgot or didn't understand permutation. So here we have to put letter. Suppose we start from this one in that plan. So first we put letter here, then we put letter here, then digit here, and digit here. All of them are different. How many letters do we have in the English alphabet? 26. You can choose any letter and put it on this position. So we have 26 different ways, different choices, right? Now, after that, you take another letter, but it must be another, not the same. So you have only 25 letters, and you have the number of choices is 25. So you write 25. So therefore, 26 times 25, this is the number of ways to choose 2 letters, two different letters. Now, after that digit, you can use the first digit with 10 different ways. After that, you cannot use that digit here, so you have only 9 digits. Remember that there are 10 digits from 0 to 9, 10 of them. Now, once you use one of them, say 5 here. Okay, then 5 cannot be used anymore, and only 9 digits can be used. And after that, 8. So therefore, you have to multiply all of those, and the answer will be 468,000. That number is a big one, and it is not as important as that product. This product shows that you know how to find the number of ways. But now let's look. What is 26 times 25? Okay, if you, because they are distinguishable letters, you actually, for those 2, you use permutations, and you choose from 26, you choose 2. Okay, why this is the same? What is 26 choose 2? Is 26 factorial, or 26 minus 2 will be 24 factorial, right? This is how you have to solve. Okay, look again here. 26, okay, if you write 26 here and 2 here, 26, and this 26 minus 2, 24. That's what I wrote. But what is that? It's 26 times 25 times 24 and so up to 1. But instead of doing that, we see that 24 factorial is already the denominator. So we, instead of writing all the numbers up to 1, we just write a shortcut notation, 24 factorial. Right here also 24 factorial. Cancel them, and what do you see? You see exactly this product. Okay, actually we started there, but now we'll finish. Now, what do we do for the digits? Also, the digits are distinguishable because they do not repeat. So you take again permutations, and you choose of 10, you choose 3 of them, right? So here is 3. Okay, here is 2. Use 2 letters, and this 3. So P 10, 10 permutations 3 out of 10, and that will be this product. Now again, what is this? It's a 10 factorial over 7 factorial, the difference. But what is that? It's 10 times 9 times 8 times 7 and so on, but because 7 factorial is already here, we just write 7 factorial. 7 factorial and cancelled out. And what do you get? 10, 9, and 8. Exactly what we had. After that, you multiply and you get, okay, you get the answer. Okay, clear, right? So we have 2 parts. One part for letters, second part for digits. And important that the first part and the second part are homogeneous. That's what I told, what I stressed, underscored when saying about the fundamental counting principle. The task must be homogeneous. If you consider the whole task, it's not homogeneous. You have to deal with letters and with digits, which have different nature and different alphabets. So alphabet with 26 characters and this alphabet with 10 characters. So you have to split into 2 parts and then multiply this and that. Okay. Okay, next problem is how many 4-digit numbers can be written using the numbers from the set. Okay, so you have digits. Digits are from set 1, 3, 5, 7, and 9, odd numbers, odd digits. And you have to get 4-digit integer. What do? Okay, repetitions are not allowed. So let me just write distinct digits. Okay, so what is the number of 4-digit integers with distinct digits? Because distinct, you see order. So therefore, let's solve this in the standard way, as if you solve this problem without knowing permutation. You have 4 positions. Okay, you choose 1 digit from here. How many digits you have? 1, 2, 3, 4, 5. So we have 5 possibilities for the first digit, call it A. How many possibilities for digit B? B is not equal to A. So therefore, if you pick, say, 3, you cannot pick 3 anymore. So therefore, if you pick 3, you have to cross it. But you don't know which digit you used. That's why you have 5 different ways. But once you pick A, B is not equal to A. So therefore, 4 possibilities are left over. Now after that, letter C, okay, digit C is not equal to A and not equal to B. So therefore, you have 3 possibilities. And after that, you have 2 digits, okay, they are left over, and you pick one of them, 2 possibilities, either 1 digit or the other, 2. So now you have to multiply, and this answer, by the way, 5 times 4 times 3 times 2, if you multiply by 1, you'll get 5 factorial. So the answer will be 5 factorial here. 5 factorial, and you know this number is 120. So this is the answer. But 5 factorial is a little bit incorrect. If you had one more digit, the answer would be the same, 5 factorial. In this case, the first digit is taken automatically with one possibility. But here is a little bit different. So what you have to do, take here, you have to take permutations out of 5 digits, and you pick only 4 of them. So what is that? It's 5 factorial divided not by 4 factorial, but the difference. So difference is 1. So divide by 1 factorial. And you see, what is that? It's 5 factorial, as I said before. Okay. So 120. Okay, so I told n choose 2, so on page 10 it's written as combinations. Okay, that formula is written so in a little bit different way. So let's look. The number of permutations equals the number of combinations times k factorial. We just involve order. But if you want to exclude, if you write without the order, n choose k, which is n choose k. This will be p permutation n choose k and divided by that k factorial. So this is the formula which is given on this page. Okay, so suppose you have this equation. Actually, we already calculated 6 choose 6. Okay, 6 choose 6 is 1, but say 5 choose 3, or 5 choose 3, what is that? You have to write 5 factorial over 3 factorial and 2 factorial. And so what is that number? Okay, you write 5 factorial. Let's write this one. 5 times 4 times, and then we see 3 factorial, the bigger one. Multiplied by 3 factorial. Okay. 3 factorial here, and 2 factorial we just write it as 2. And 3 factorial cancelled out, so the answer is 5 times 4 divided by 2. Okay, it's 20 divided by 2 is 10. 5 choose 3 is 10. But if you take 5 choose now if you take 5 5 choose 2, okay, 5 choose 2. Okay, agree that to write that symbol is much easier than to write C, 5, 2. Sometimes it's written also in that way. C combinations, okay, 5 and then 2 out of 5, that way. So in some books, old books are used that one. But new mathematical books use that one. So what is that? It's 5 factorial. Now we have to write 2 factorial and 3 factorial. But you see, 3 factorial, 2 factorial, 2 factorial, 3 factorial, we multiply them. The product doesn't change. So therefore the answer is the same. 10. What does it mean? Now, how to formulate this in words? Okay, that equality says, and also, where is that? And also, for example, this equality says the number of ways to choose 3 objects out of 5 is the same as to choose 2 objects out of 5. They are the same. Here, it says the following. The number of ways to choose 3 objects out of 3 is the same as to choose 5 objects out of 5. So, another interpretation is as follows. If you consider the number of 3 subsets with 3 elements, it will be so many subsets. If you consider the number of subsets with 5 elements, it will be so many subsets. And these numbers are equal. Now I want to explain to you Why this is the same? Actually, I already explained this using marbles, but now it's time to explain in this particular case. For example, let me just explain. Let's write. It's not in here, but it's very important to understand why these numbers are equal without any formulas. Okay, why 5 choose 2 equals 5 choose 3. Even without knowing the formulas and nothing. So the only what you have to know is the meaning of that. 5 choose 2, it means you choose, okay, here is what? Choose 2 objects out of 5. Okay, that one means choose 3 objects out of 5. The only that information will imply that these two numbers are equal. The number of ways to choose 2 objects of 5 is the same as to 3. Okay, let's consider this object. Suppose this, okay, you have 5 marbles. 1, 2, 3, 4, 5. And some of them, and you color. So some of them are white and some black. Okay, so 2, let me just write 2 white, okay, and 3 black. Okay, now here you don't know where, so you put these 5 marbles in one row, you line up. So how to do that? Suppose so what do? You pick 2 positions, suppose this position and that position, and put white marbles in here. It's one way. Now what happens with the black one? The other positions are determined uniquely. So therefore, the other positions will be that one. So if you pick some positions for the white marbles, you automatically picked 3 positions for the other for the other ones. Okay, so you got it. So you consider the complement. Okay, this is a set. In this set, so you have 5 possibilities, and then you color, and and then you color 2 of them, any 2 of them. So some 2 of them in white. So suppose this one and that one. Okay, they're white. And immediately after that, the other 3 are colored black. This is another one. So if you pick 2 of them, then 3 of them are already picked. And so if you pick the 2 of them with so many ways, then automatically the black marbles are taken. So it's chosen in the same number of ways. That's why they're equal. Is it clear or not? So let me repeat once again with 8 and 3. So you have 8 marbles. 3 of them are white and 5 are black. Suppose I pick, so 8 choose 3 means the number of ways to choose 3 white marbles. If I choose 3 marbles, white marbles, then what should I do with the black marbles? Just put them in the remaining places. So therefore I have, so if I have 8 positions, 1, 2, 3, 4, 5, 6, 7, 8, okay, and if I mark 3 of them, suppose like that, then I have to make a correspondence between the same 8 positions, but now I have to mark all the others, the complement. So once I pick this, okay, when I have this choice, okay, automatically, in a sense, I choose that. So we have a correspondence. So therefore, the number of ways to choose 3 positions is the same as the number of ways to choose all the others, 5. That's why these numbers are equal. And that's why when you show the formula, when you see the formula, the only difference is in the denominator. Here I multiply 5 factorial by 3 factorial. Here is 3 factorial by 5. And the product is the same. That's why they're equal. Okay, that's what you have to understand. Next example is find the number of different subsets of size 3 in the following set. Okay, we're close to the end, and I will consider several cases. Number of 3 subsets. 3 subsets in the set S, which is M, A, T, Meth, R, O, C, K, S. Okay, I told you many times that when you write a set, all the elements are distinguishable. Okay, so it's not like all marbles are white. This is a set of, it's a multi-set of white marbles, but actually a set of one white marble. So all of those are different, yeah? So how many 3 subsets? What does it mean? It means that you just pick. You have how many, by the way? 1, 2, 3, 4, 5, 6, 7, 8, 9, correct? 9. Yes, 9. N equals 9. And what do? You choose subsets. So order is not important. So therefore, it's combinations. So K equals 3. So the number of 3 subsets equals 9. Choose 3, or, okay, 9 choose 3. Okay, so many. So this you have to write immediately. The number of 3 subsets. Subsets with 3 elements. Okay, and you can write how many of them. Okay, the answer is this one, 9 factorial, or 3 factorial times 6 factorial. 6 is 9 minus 3. Equals, okay, 9 times 8, 7. And after that, you see 6, 5, and so on up to 1, which is just 6 factorial. That's right, parentheses. Okay, 3 factorial is 3, 2, and 1. And then you write 6 factorial, cancelled out. So the bigger number, it's better to cancel out the bigger number. So it will be that number. Now let's continue crossing. 9 and 3 gives you 3, this is 1. Okay, and 2 gives you 4. This 1. So now please rewrite, otherwise you cannot see. I also recommend you to circle the remaining factors which you have. So it will be 3 times 4 times 7, 12 times 7 is 84, correct? Yes, correct. 84 ways to choose a 3 subset. So suppose you pick, by the way, so suppose, okay, so if you write the whole list of all the 3 subsets, for example, one set is MAT, another set says MTH, okay, and so on, and one of them is CK and S. So if you write all of them, the whole list of all possible, like MRC, or ATS, or ATH, or ATO, and so on. If you write the whole list, you will get exactly so many, namely 84 and 84 positions. But now, if you pick one of them and then exchange the letters, you can do this in 3 factorial different ways, which is 6 ways. MAT, MTA, and so on. They are different, but not from the set point of view. From set point of view, it is the same set, the same bag with the toys labeled M, A, and T. Okay. Now, next problem is a little bit just application of that, a little bit non-abstract application. A common, I will not write it down, but I will formulate. A common form of poker involves hands. Okay, hands, it means sets. Okay, that's what you have to understand. From a mathematical point of view, it's sets. Sets of 5 cards each. So set, now let's call it 5 set. It means 5 cards. 5 cards at a time. Okay. This we call 5 set. From a deck consisting of 52 different cards. So N equals 52 cards. Okay, how many different 5-card hands are possible? So what do? You put 52 cards, okay, in one line, and then you pick 5 positions. This will be your hand, your set. So the answer is number of ways to choose 5 cards. Important that all the cards are different. Okay, you can distinguish so 8 from the ace and king from the queen, right? So all of them are different. That's why it's important to take. The number of ways to choose 5 cards. Okay, this is the same as to choose to pick 5 places. 5 places out of 52 total. Equals, okay, you choose 5 of 52, 52 choose 5, 52 factorial over 5 factorial, and minus give you 47 factorial, this multiplication. Okay, how to calculate? If you take your calculator, most likely your calculator will not be able to calculate 52 factorial. This is the product of 52 numbers. But instead you have to solve this way. 52, 51, 50, 49, 48, and so on. But now we see, 47 is here. So you just write 47 factorial instead of writing all the numbers to the end. Divide by 5 factorial. It's 5, 4, 3, 2, and you can write, you may write and may not write, but let's write 1. 1, 2, 3, 4, 5. Okay, so actually, yeah. And times 47 factorial. And 47 factorial cancelled out. So we did this many times today. So how to calculate? It makes sense, I guess, the following. 5 and 50 gives me 10. Now 4 times 3 times 2 is, what is that? 12 times 2, 12 times 2, 24. And this is 48, right? So it's, when you cross, you get 2 here. So the answer is 52 times 51 times 10, okay, times 49 and times 2. Okay, then you take your calculator. Now calculator is applicable here. Or you can multiply in column, as I told you many times. This will be 2,598,960 possibilities. And that's why it's very difficult to predict what, okay, which 5 you took. Yeah, by the way, the total number of possibilities, the total number of ways to put 52 cards is 52 factorial, right? Okay, so if you want to find the probability of 5 hand, you have to 52 choose 5, divide by 52 factorial. And what is that? 52 factorial over 5 factorial, 47 factorial, and divided by 52 factorial. So 52 factorial will be the denominator. brains without, and you had a very, very small number, 1 over 5 factorial times 47 factorial. So you have to multiply, this is 120, and this is a huge, huge number. When you divide 1 by that, it's almost 0. It's a little bigger, but almost 0. So the probability is small, and that it shows that the number of hands, you have so many ways, and the number of ways to put 52 cards is 52 factorial, huge number. And the ratio of the number of possible numbers for hands divided by the total number of numbers is a probability. That's how probability comes up with the formulation. Okay, the last page, number 15, is the most important. I put it in D2L, and also it's in the book. Okay, and I highly recommend you print it out or just rewrite in the notebook. It's written in which case you can use permutations and in which case you use combinations. Remember, combinations is the same as sets. Sets means no order. Okay, order is not important. That's why you divide by k factorial and n minus k factorial. But combinations, permutations, order is important. So therefore, if you consider the order, then you have to multiply by the number of orders, which is k factorial. Okay, so I finish this chapter now, and now the next chapter will be, the next section will be Pascal's triangle, and we'll start, we'll do this after that. So, thank you.